Sniffles.
Okay, the really gory details of orbits, in particular Coulomb orbits, what we're going to do is compare side by side through most of the lecture. We're going to compare the harmonic oscillator, its horrendous algebra, and even more horrendous algebra that goes with the Coulomb potential. So this is a knockdown, drag-out lecture of algebra and a little bit of geometry at the end. I want to compare that whole way of looking at orbits with what we'll do on Monday, in which we'll attack the problem in much the same way that we attack the coupled oscillators, using group theory, basically, using the symmetry. We'll see a little bit of the shall we say, earmarks of symmetry as we go through the algebra. But most of what we're going to do today is stuff that you might do in an advanced, well, maybe not sophomore physics, but certainly junior mechanics if somebody was really... Now, orbits, you think, well, that's all everybody knows about orbits, but it's really become something of an interesting thing for people interested in GR, because almost every galaxy has a black hole, and it has a few unfortunate, maybe fortunate, depending on how you look at it, stars or planets or bodies orbiting this enormous Coulomb field. And instead of taking months or years to make an orbit, they do it fairly rapidly, sometimes in a day or so. They make a nice Coulomb orbit. The other reason we want to learn about Coulomb things is because the main thing that got us started in modern physics was Rutherford's scattering experiment, in which alpha particles showed that the atom is mostly nothing, mostly electrons. That took a while to really understand, but that the fact that the nucleus is so tiny was really a surprise to everyone. And Rutherford's the one that got that going. And it's the algebra that we're going to be talking about today. Now, we don't have many demos. We've already seen these. I'm going to start them up again. But the first page of links, there's the isotropic harmonic oscillator and the Coulomb. That's now there's this guy too. We'll maybe talk about that toward the end. In any case, let's get started. It all starts with a conservation law, something that makes it possible for us to do these two. The fact that they're isotropic in space, the harmonic oscillator, IHO, isotropic harmonic oscillator, and then the Coulomb field also. A potential that's totally a function of radius. We're going to use the letter rho to, for the radius throughout most of the lecture. There'll be a few times when we switch over at the end when we do the elementary geometry. In any case, what's possible here with this, and I want to emphasize the angular momentum conservation that goes with the symmetry of isotropy of space, in this case, three-dimensional space, lets us define a constant that makes it possible to do an effective potential that is only one dimensional. So we have mentioned this already, and the two that we're going to talk about are shown in the screens down there, and we'll get to that complexity in just a minute. But the basic idea of having a kinetic energy and then conservation of angular momentum that goes with the kinetic part of the angle, it gets rid of the angle, so we don't have to worry about it because this quantity is constant. And this is true for all isotropic, all central forces. That's what things that only depend on radius. So the parameters that we work with here, I'm using the Greek letter mu for the angular momentum. You might think, well, I should use m, but you know darn well we got to deal with a mass, so that's the parameter that has an m. And then this is the good old k that we've been talking about, a spring constant if you'd like, but it's only a spring constant on this side of the screen for the harmonic oscillator. So that potential is going to be occupying this side of the screen as we go through for at least, well, I should say, a good part of an hour going through the algebra of these two creatures side by side. And it's really quite enlightening what you learn by doing that, by going through and doing both of these creatures. If you like to think of them as that, Coulomb and IHO. So let's get the sort of the conventions down right here. This constant, the plot that we're dealing with and the structures that we'll deal with today are just the attractive Coulomb potential. So this particular plot is showing negative values of the potential, and the spring constant there, K, will be taken as positive. This is convention for both sides here. So remember that if you change the K to a negative value for either one of these things, blows up. Okay, you talk about a repulsive thing. The only time we've worked with a repulsive potential was in that problem that involved the rotational model of the trebuchet, in which you fell off on a parabolic potential that was upside down. Here, they're all right side up, and they're making bound states. That's what we're going to talk about today. We'll get to the others in the lecture on this coming Monday. So, I want you to note that convention. It's a little bit different from what you might see in books. Attractive K is positive. That is, if minus K is negative, we're talking about bound states for this Coulomb thing here. Here we have no choice. Everything we're talking about here is bound. This is an attractive harmonic oscillator. So, this is what we did back in lecture 7. Remember the 3 steps into or out of hell. And the isotropic harmonic oscillator was here. Then all the rest of the space was taken up by an isotropic Coulomb potential. And we'll make some connection with this. This is where we get into doing this thing for real. All right. Now, one of the things that you need to do in order to make all this work, and this would be true if we were doing some weird potential besides these very highly symmetric potentials that let us solve things right down to functions that describe the orbital motion, which requires the symmetry that these two have beyond isotropy of space. The stability radius, that point right there, and in these cases, a bottom point to every one of these effective potentials. Whatever value I set for these, whatever energy I decide to use, as long as I'm on this side of the line, I'm talking about attractive, and there will be a minimum somewhere because this thing goes to infinity as you approach 0. So all of these potential curves here take off, whereas this is much more well-behaved. It takes off as well because of this part of that potential, but if I were to set that angular momentum to 0, I would just have a parabola here. And if I set the angular momentum to 0 here, I've just got a Coulomb field that goes to infinity in the negative direction. So the basic idea then is, as you can see just from what's written here, is that I'm looking for the zero of the derivative of this for these particular constants, mu and k. And that works out to be, if I solve this equation here, mu squared over m is kp fourth. Over here it's mu squared over m is equal to k rho. Okay, this is rho, not p. K rho to the fourth, and here it's k rho to the first power. Okay, so this is what we're going to do for the next probably 45 minutes, is we're going to do various things manipulating the algebra of this, and we'll compare these two symmetry monsters, you might call them. Okay, now oscillation frequency is the next thing we're going to need, and that involves a second derivative. Once you've gotten this particular stable point here, what you want to know is the curvature of it. This has some really kinky curvature right in this region, although it's getting kind of flat there, so that changes very, very radically as you go out to higher bound states. And here it's not too different as you go up the line here. Partial derivative is more well-behaved function. In any case, the stability radius, the point where you get circular orbit, is given by the square root of our angular momentum divided by the square root of mk. So this is a little bit more complicated expression than the one that this comes up with, which is rather more, shall we say, friendly, and that is the radius is simply the angular momentum squared divided by mass times the constant k. This one has the mass times the constant k with a fourth root of that. It's two square roots. Okay, one square root of the angular momentum. This one's got the angular momentum second power, not half fractional power. Okay, so next step is to figure out how the curvature goes at whatever point this is. I'm going to use that point. I'm going to substitute that right into this expression for this second derivative of our effective potential. I'm going to do the same over here. So when I stick that in, if I stick this mu squared in, I can write an expression that looks pretty complicated at first, but it really simplifies. So you see the results here, and you might say, hey, isn't that a typo? This k over m square root, we recognize that as the frequency of a harmonic oscillator. But let's remember that you get 2 tries at that as this thing goes around, whereas you don't here. And that's something I should probably show by doing a simulation again. I think we've talked about this once before, but it's worthwhile. In any case, once you realize that, and that's correct, the angular orbital frequency for this thing, that is phi dot, that comes out of this, is just 1 times k over m. And then this guy down here, this is an interesting thing. Here, the angular frequency, that's the angular momentum divided by the m rho squared. That comes out fairly simple, but it's just a mk squared over mu cubed. That's kind of a little weirder than what we're familiar with, but we'll make the connection later on. So what we discover here is that the angular frequency, this thing here, and the radial frequency, the frequency around the stability point, that's 2 to 1 here. Here it's 1 to 1. So this is, both of these are integer relations, integer ratios. And so this is guaranteeing that every orbit that we make in this region we're talking about here is a single orbit. It doesn't make Lissajous patterns. It just goes around and connects perfectly every cycle. closed orbits, okay? A result of the extra symmetry this has besides space isotropy. All right. There's also interesting things here, just to look at the expression for the force of a harmonic oscillator. If it's the harmonic oscillator inside the Earth, that thing right here over M is omega squared R, but that omega squared is this thing, okay? Gm, whatever mass the Earth has up to that particular radius, and divided by R cubed. So we get here an omega that's the square root of the K of the harmonic oscillator. We're looking at the K, that's this constant right here. Whereas this guy over here is the square root of that constant divided by R cubed. Okay, that's the frequency, you see. So we're getting our 3/2 power law here for the angular frequency of all of the orbits that are bound. That's kind of neat to get that right away. We'll go and do it. We'll do the whole study of the time behavior more toward the end of this lecture. But you can see the algebra. This is what most of the screens are going to look like today here, full of algebra. But the real idea is to compare these two symmetry monsters. All right. Now, I say that the symmetry monsters because there's a mystery that emerges after we do the next two steps here. And that is, we will come here and take this thing one step at a time. But basically what I want to know is, okay, so if I'm going to be oscillating on the radius here, and it's always going to be given by a very simple formula, I also would like to know for a given energy that I might be talking about, particularly if I'm talking quantum mechanics, if I'm talking about a wave function that's going to obey this potential, I'd like to know the turning points. I'd like to know if I'm oscillating back and forth here, well, how far do I go? Up, and how far in? Out, in, back and forth, okay? And with the harmonic oscillator, we've already talked about that it has the same deal. We need to know where these things turn around. Because if there's going to be a wave function for this in these coordinates, it's going to wiggle in here, and it's going to evanescent exponential wave function outside. That is, it's going to die off on the high and the low side. Okay, so that's another class, of course, class in quantum mechanics of harmonic oscillator, looked at in polar coordinates, or atomic physics. That is very much of a consideration as we do atomic quantum mechanics. Okay, so the classical turning radii are exactly those places where this kinetic energy part of the radial energy is zero. So if I can get rid of that thing, I just have a simple, well, maybe not so simple equation to solve, but it's quadratic. This one is pretty obviously something a little bit more than quadratic, but it is a quadratic equation in rho squared. That one's a quadratic equation in rho. So there's a big difference right there between doing the oscillator and the harmonic oscillator and the Coulomb. Okay, next stop here, to go ahead and solve that. So we get an equation looks like that for our friendly oscillator. The Coulomb, it's not so terribly bad. Okay, it's a very nice quadratic equation in the radius to positive powers. This one's a equation in radius to negative powers. Okay, and it's the quadratic equation in rho squared, whereas that one's just in rho. Okay, that's neat to see that. Okay, and I've never seen anybody do this. This seems to me this would be the absolute thing you have to do in order to make sense out of the two potentials that occupy almost all of our physics, at least at the elementary level. Okay, the old-fashioned modern, non-modern physics. Anyway, here's where the mystery comes. We go ahead and we solve these two quadratic equations, one of them for a rho squared plus and minus, okay, and here a rho for this plus and minus. Plus is high side, minus is presumably the low side, okay? And here we're talking about, if we're going to put this thing in, let's see if I've got that right here. I've got to see if I got that 2e k mu squared, k plus or minus. Okay. May have made a little bit of a boo-boo here. I've got the rho plus and minus here, then I've got 1 over rho squared. Basically what I'm doing is making a connection between, this is the rho plus and minus squared, or else 1 over rho plus and minus squared, which I change here. See if that's a little bit of a puzzle. But in any way, in both of these expressions, if you write both of them as 1 over rho plus or minus squared, you discover that the energy of this one is replaced by the spring constant, the potential constant for this one. And you see the E here being replaced by the K squared, okay? And then the K is replaced by 2E. So twice the energy shows up over there where the K is. Okay, that's kind of neat. Okay, and everything we do from now on that involves this geometry of turning points will have this property, and it's quite remarkable. Now, one of the things when you read through this lecture on your computer, I've got a lot of links here to take you back and forth between, I think this is page 34, but if I click on this and go to page 62 just to see where we end up here after doing a complete calculation of this thing, the turning points showing up here for the actual orbit equations. That's what we want to derive, but this is part of that derivation. Now I'm going to click back to 34 where we were, but this is where it starts. This is where the algebra gets a little bit hairy. So what I want to do is write a polar coordinate equation for the orbit. And because of symmetry, we get to do that. We get to write a polar equation where the radius is given in terms of the polar angle, or vice versa, the polar angle is given in terms of the radius. So here we are back with our effective potential kinetic energy equations. And the trick to doing this, that is the trick to finding rho as a function of a polar angle. And if you're going and studying this later on and you want to click ahead to the physics table where the physical quantities of each of the orbits, but in particular the Coulomb one is the one that's the most difficult, and that's the one you'd probably be clicking ahead to see. You can do it, and you can click back. You always have a place where you can come back to where you were, more or less. Okay, now the other thing we can do, and we have to do this, and this is even hairier than what we're about to do here with the coordinate equation, is the rho as a function of time. For the Coulomb, that's a real help. For this one, we've already done that. It's really simple. Just draw those two circles and let the thing swing around, and you get your time solution very neatly. But it isn't until page 90 that we really write this down to this thing. And that has a geometrical construction. It's very similar to Kepler. What's the name of it? I'll think of it in a minute. But the idea of having this geometry, something goes around at a constant rate, and it drags something that's going in a very non-uniform motion.
Anomalies.
So there's something else to click on, but I'm not going to do it right now. It shows you where this thing starts and ends. Anyway, the trick to this right here is to make use of this equation that relates the velocity, the angular velocity, to the radius. And that lets us make an equation that finally is just radius as a function of angle. So that's what's going on here, is I'm taking here the oscillator one and here the Coulomb one, and writing a differential equation involving just v and rho straight away. Okay. Well, at first that looks like it's going to be a real mess, especially for this one. That one not so bad, but still fairly complicated. And we need a new variable in order to make it a little less messy. This one comes right away, as does that one, with d rho over rho squared. But I can turn d rho over rho squared into du. If I can do that, yeah, I sure can. I just have to write u as 1 over rho. So that gets us a not so bad looking thing that can be integrated, and we're going to talk about that. As we talk about this one, which is a little bit more problematic. It's got an inverse u squared in there and a u, non-inverse u squared. This one's got a u and a u squared, both in the numerator of a square root that's in the denominator. Okay. Just to make things complete, we go the other way here and define an x that is the square of u, and that turns out to help this one maybe more than that one. But these are two avenues that you can take as you look for ways to integrate the differential that's resulted here. So here it's written in terms of x, and it's got a nasty square root of x in it. But this one, it's got a square root of x out here, but it's not inside the radical. That's not so bad. It looks like we might have a chance of integrating these guys, both of them. Okay? And there's the similarity again, just to see that once again an e on this side becomes a k on that side, everywhere that it is, it's only in one place, and then the k, which is just there, that k becomes 2e over here. Okay. So as you go through both of these, working them out for the first time, you have a check. You can see if you're getting the right answer, if this similarity works. Okay, well, we're getting into the thick of it now. What we have to do is look at quadrature intervals. What are the quadrature interval techniques? And we enjoy having an interval that's elementary. This is really not much different from the integral that you get if you were to just do z squared and call that a squared. You're all familiar with that as an arcsine integral. Well, this is going to do the same thing. But of course, the roots of that quadratic equation are what are going to play a role here. So we're going to be talking about a plus and a minus and let's see if I've got, it looks like I should have put x minus x plus here and x minus there. Anyway, the z's are what we're interested in. We've got a large z and a small z. Large z being the aphelion, and then the perihelion of the orbit will be this one. And as we mentioned already, the oscillator is going to have 2 of those. But that doesn't hurt the algebra. I can still use this same technique on both of them. So we're going to define z plus as the sum of a constant alpha and z minus as a difference of these. Apogee is what we're really talking about there. Okay? So this particular solution is based on just a quadratic equation in either case. We're going to be able to use that. So the idea will be that then this will lead us to an equation of the angle as a function of z, the z being the, could be the variable phi, or maybe some combination of that in the radius. That's what we'll have. Okay, now let's see if there's anything. Yeah, the variable z could be rho, or maybe it's u, okay, or it could be rho squared, or 1 over rho squared. Any of those are possible variables. We'd like it to be a rho, because that's the radius. But 1 over rho would be too bad. Anyway, that's what we're playing with right here. So basically what this is going to do for us in both cases is give us a solution that looks like that. That is, we're going to get that the whatever it is that you're calling z, it is 1 over rho, or a power of that, okay, is going to be this beta constant, which is a difference of these two roots, and sine of, well, these a and d quantities that we will be dealing with very shortly here, but anyway, we already have them as the coefficients of the quadratic equation itself. In any case, this is going to give us some sort of curve. It might go this way, or it might go that way, it depends. This is basically what's going to take care of all of the problems, bound or unbound, and Coulomb or oscillator in 3 space. Okay, so this is where we set it up, because we have to do it to this equation, and we have to do it to this one. So we have to assign the A, B, and C to whatever we're interested in as the variables here, x being u squared, that being 1 over the radius squared. Then over here, it's a little bit simpler. We're working with a z that might be 1 over rho. That could be our dependent variable. And when we do that, the classical turning points will be this and this, so we can make connection with those. We just listed those a few minutes ago. And the basic idea is that A, this guy right here, mu squared over m squared, and then the B, that's the thing that's multiplying the variable z, it happens to be x right here, okay? And then finally C is this last guy, and then D is the coefficient of the whole thing. This guy right here, mu over 2m is the D, okay? So, all right, we've taken care of the oscillator. If we just put all that stuff in there and do the algebra right, we're home free. This one a little bit, much the same really. Let me make sure I'm following along on both these screens here. Let's get this thing on both screens so it's easy for people on both sides of the room to see. That alpha constant is of interest here. We're going to do some algebra to get that. This is really the hardest part of this particular development that we're doing here. The algebraic details are in a few pages. But the basic idea is that when we get these quantities, go ahead and do the minus b over 2a, and then this thing, b squared minus 4ac. I've got to put these guys in there, and that's the hardest part of this algebra. It's about equal amount of labor on both sides. Okay? I think that's it. Anyway, the result after going through was, I'll just show you in a minute here, and I'll put that on that screen there. In fact, I will go ahead and take this guy all the way to where we are right now, which is about there. There's the algebra that we're working with, and that's the thing that lets us, using the turning points to get the solution. So this one comes out to be a constant, and then a coefficient of the sine of -2 times the angle. Whereas this one comes out to be a somewhat different constant, and not that different. It's got the k here instead of the e, okay? And then this k becomes 2e, all right? So that little supersymmetry starting to show itself there. And then we have a coefficient, again, times the sine, and this time of just phi. Now, sine of minus phi is minus, so this should have minus sign there, and so will this one, but minor detail. Okay? So, that's the thing, and the idea of that comes after you've solved this algebra that's showing right here. So I'm taking those A, B, C, and D and make them into the form that they'll fit for the alphas that define the equations. All right, okay. So let's look at the details of what these guys are giving us here. This is the algebra. Right away to the geometry, what we've just derived here. And this is kind of easy because you don't usually think of doing this with a harmonic oscillator. It's so simple, just do sines and cosines. Maybe you might do this in a case that you're going to apply a magnetic field or something to the orbit. But you know, polar coordinates for an ellipse, that's pretty weird. Okay? Now this is the general form of a polar equation for an ellipse, okay, or circle. Okay, polar coordinate for a circle that's off center. Kind of like those things in the problem that involved the tunnels and the cars that went through the center of the Earth, which is the isotropic harmonic oscillator. That's what this. But it's 1 over rho squared. You see that comes here. Here we're looking at 1 over rho without the square. But the same deal about the k's and the e's is happening there. Okay, so now this is the guy we have to discuss as far as the geometry, because it really is important to get the geometry of a Coulomb orbit into polar coordinates. It really doesn't make much sense to have this thing in Cartesian coordinates, unless you want to keep changing the origin for the Cartesian coordinates, okay? Because this thing's off center. These nice orbit here, always center, no problem. So polar coordinates really are what the doctor ordered for the Coulomb. It's not ordered here, but the fact that I can do it is sometimes useful. All right, let's see if there's anything else I need to say here. Yes, we're getting to the point where we're going to use those turning points, and this lets you click back to where we defined the turning points for the first time, or click forward to where we'll really be using them. So that's something that's, I think, I've worked very hard to make this lecture something you could study all of this with. There's the whole list of the various relations that these two potentials have with regard to their constants and their turning points. And I mean the constants that ellipses are defined by: major and minor axis A and B, eccentricity, epsilon. All of that stuff is about to emerge here. But in this case, what we're doing is just looking at the actual geometry of this, and in particular this one, where 2a is the major diameter of the orbit, and that 2a has, as we're going to explain, we're going to go through this geometry of polar parameters. This particular cutting point right here, remember, for a parabola was called the lattice radius, okay, and then there was if it was an ellipse, a minor radius, a parabola didn't have that, but now we do. So the minor radius and the major radius are things that you're familiar with as Cartesian coordinates for an ellipse, but this ellipse is off-center, so we have to be careful. We have to make use of, whatever this particular circle is right here in its geometry with respect to the thing. Now, what we're going to see fairly easily, the interfocal diameter, we have to show that that's the difference of these aphelion and perihelion. Well, that happens to be 2a epsilon. We'll get to that later on as well. But all of these pieces here are very similar in some ways to what's over here, except that over here you're using radius squared all the time, and you've got that little 2 there, making that thing much simpler as a geometry. Okay, now let's take on the polar nature of this. And I'm going to move the screen down there ahead to this. And I think that's about there, right there. So I'm going to leave that one alone. But now I want to take on the geometry, the polar geometry that a Coulomb orbit has. We know enough about the oscillator that we don't need all of the things that we're going to do with this, but I want to show you that the parabola that we worked with before has an epsilon, that's an eccentricity of 1. So this is just a generalization of what we worked with before. If you recall, a parabola would have the same distance to any point on its orbit. And this is kind of looking like a parabola for a while here, but it's not one. It's an ellipse, obviously, and that means that this epsilon here is making this distance. Epsilon is less than 1. This distance here a little longer than it would have been if I would just have a parabola. If I just had a parabola, it would be r here and r there. But now it's r over something that's less than 1 makes it bigger. And the idea is that all of the conics, every one of them, is defined in this way using epsilon. So if I make the epsilon bigger, I can make a hyperbola here, in which case it will bend up and make this distance smaller than this distance. And then, of course, there's the parabola, which divides those two classes very conveniently. Now, the other thing that's going to happen here is we've got to make a connection between all of the parameters that we can have here, and there are a few more that I want to throw up here, various combinations of the 2a, the b, the epsilon, the lambda. All of that is coming now. We've got to make sense out of the geometry to match with that of the algebra. Now, at this point, you might say, my God, this is complicated. I didn't remember all this stuff being complicated. Well, it is, because we're doing it the old-fashioned way. Next Monday, we bring in the epsilon vector, which is the analogous to the Stokes vector in the oscillator business, and things clear up. We get all this basically for free. But I shouldn't tell you that, because then you say, well, I don't even want to listen to him anymore. I want to take you through the geometry of conics, just so that you have that, because it's there whether you use the fancy mathematics of group theory or not. So here's the idea of this, and that is, if I go to a certain point here with an angle phi, that means this angle is equal to that angle because of the parallel lines, I have right here a distance r cosine phi, which is very nice. And I have r sine phi here, but I'm not going to use that right now. I'm interested in is writing the equation just in terms of r and phi, and that's all I need, because I know that this distance right here is r over epsilon. And this distance right here, with an r that's equal to the lattice radius, and that's the other parameter that we've got to get used to now, as we did with the parabola, this is going to be lambda over epsilon. And then if I have any radius inside there here, well, whatever that radius is divided by epsilon will be the distance to that point. And so forth, all the way down to here, where I have a focal distance here of, we'll call it r minus, and this has to be r minus over epsilon. So all of that radius business with the epsilon, which right now is 0.75, so this is a 0.75 eccentric orbit. The Earth's orbit is very close to 0. It's like 0.016 or something. Do you remember the eccentricity? Okay. Anyway, this is a big eccentricity, really obvious list. And as you approach 1, you get into those orbits that involve comets. Halley's Comet, for example, showing up every 70 years or so. Okay, so that's kind of what we want to get our head around, is that. In any case, by equating these things, letting the r equal lambda plus r epsilon phi, solve for r. Okay, there's the solution right there, lambda over 1 minus epsilon cosine phi. Or, we've been talking rho before. Remember, 1 over rho is important for us. 1 over r, okay, is this. So this is the inverse equation of the ellipse. So what you get is 1 over lambda minus epsilon over lambda cosine phi. That's the inverse radius equation, okay? Now, I'm not going to click on that, but when you read this, you go ahead and do it. But the basic idea is that I know my lattice radius. I can get that fairly easily by just taking my equation that I've already derived for 1 over rho, okay? And this is the formula that we derived. I'll go ahead and see if it works on this computer just for the heck of it here. Let's just go ahead and recall page 66. And there it is for our Coulomb orbit. 1 over r is this spring constant over angular momentum squared, and then this radical here, another omega angular momentum squared divided by m. Okay, so that is thing. Now, I'll go ahead here. The turning points are there, and then a little bit further along, oops, wrong computer. A little bit further along, I better go back on that one, so I'd like to keep that. We have what we're doing right now. Okay, so this lets us get r minus, r plus. That's an interesting place. Those are the aphelion and perihelion, rho minus, rho plus, okay, or radius plus, if you use the old-fashioned English r instead of the Greek one. And this is interesting too, the sum of those, go ahead and add them up, is the lattice radius divided by 1 minus epsilon squared. That is a key relation. And also the difference between these two, and this is really important right here, and this is where I'm talking about the parameter table to match this to the physics. We'll skip ahead to that shortly here. But if you don't learn anything else with this lecture, and that's entirely possible because it's a fire hose of algebra that's coming here, if you don't learn anything else, be aware that the total energy of any Coulomb orbit, not just this friendly ellipse here, is the Coulomb constant divided by twice the major radius. That is, the Coulomb constant divided by the diameter, the major diameter. Whatever that is, for hyperbola, parabola, or ellipse, or circle, all of the conics. Okay, this is really cool. Now, you have to worry about the sign here. Remember, our convention is that this thing represents an attractive thing. The minus should be there. Okay? So we're talking about energy that's below zero. This thing is definitely positive. So we're talking about something that's bound. It's negative energy. That's what you think about it in quantum mechanics. Okay, so negative energy means. It means you're going to stay home, not going to run off and get in trouble. So I say this is a really important part. It doesn't care about the beam. It doesn't care about this distance. That's associated with angular momentum. This is associated with total energy. Okay, and this is a Cartesian parameter for this ellipse. It's different. Now we're going to make connection between energy and momentum with the polar parameters, the lambdas and the epsilons, and that we'll certainly do here. We already started that right there in the rho plus and rho minus and all that. Okay, so we want to do that, make that. Very important result. But we've got a couple more that are also important. As I go ahead and find out various things that I can do, I start putting difference here. The difference for this thing is fairly complicated, but you write it out. It's not so bad. Okay. There's a plus, there's a minus. Okay, so it's 2 lambda. 1 minus epsilon, this is 2 lambda epsilon divided by 1 minus epsilon. So those are two things that can connect to the physics now. This is where we make the connection, which is summed up on this table, which we'll get to shortly. There's the ratio of those two, which is kind of interesting. Isn't that interesting? I think that would really be complicated. No, that's epsilon. Okay? And remember what they are. Okay, the epsilon, the rho plus minus and rho minus. They're part of our physics here. Okay, see if there's anything else I need to add to this. Lattice radius, I can now solve for that. Okay. As I say, also important. Also important. Angular momentum. Total energy really the big deal, but angular momentum, very important for quantum mechanics. Okay. That's only a function of lambda. Not wild? Well, it's a little bit sneaky. It's also got to drag in the mass and the Coulomb constant. But this one has a Coulomb constant too, and it's got a 2, but no mass involved there. Here it is. Okay, that's cool. Okay, so those are the simple formulas that come out. There are two others that are a little bit more complicated, but anyway, minor radius can be written in terms of all these things. These are the Cartesian components, A and B, of the ellipse. Okay, and then the epsilon. The Greek is the polar parameters. All right, I think we're about there, and there is page 79 right there. Okay, I just put it here. Here's that energy formula, physical parameter. It's very important. Here's the angular momentum formula. And then there's the related to the xy parameters, A and B. Now, B is kind of a mess. It involves the mass, the energy, and the angular momentum. Okay, so it's a bit more complicated than this one, but just as important. Here's the L by itself, okay, without the energy. That's giving us the angular momentum. I put an L here. Now, I didn't use capital L except in this one place, because this class, capital L means Lagrangian. But here, I'm going to use it. Now, the actual lambda, this guy right here, is actually L squared, modulated by mass and Coulomb constant. All right? Now, it could be plus or minus, because that K could be plus or minus very easily. All right. To make hyperbole. Okay, now I'm going to go through this now, the timing of orbits. Coulomb, trivial. This is not trivial. This is Newton's great, Kepler's great discovery. Kepler did this before Newton got around to making this. Kepler didn't do the algebra. That was a Newton thing. Anyway, here is the time interval written out. These are all equations that we worked out before. I'm doing here the d rho divided by the basically the energy expression. And I don't know if there's anything I need to say on this. This kicks back to that equation, page 38. But anyway, this is the beginning of the time analysis for an orbit. Now what is really magical about this is that this, a little nomogram that we drew that involved constructing an orbit by simply drawing two circles, one for the let's call it B, because that's the one that's usually smaller, and then the A circle, the larger circle, major radius circle. And then what you do is pick any line and then drop a perpendicular that crosses the horizontal there, and that's a point on the orbit. That was the construction that we used. That involves a line that's going at a constant rate, and it's dragging this thing behind it, but it's picking up speed until finally we get here, and this point passes that, and then it's going to be on the other side of this thing, which is constant, and slowing down as it reaches the high point, the aphelion right here. So you go from falling to the perihelion and then coming back again according to that little geometrical construction. This one is a little bit more complicated. What you do is the same thing. You have here a phase angle, okay, and it drags a line coming from this point right here. Okay, so you have to know, you have to draw a point here and then go up to a circle, and there's the, it's called the mean anomaly, and this is called the eccentric anomaly, the Kepler's eccentric anomaly that goes through focal point. The focal point that's on the low side, on the perihelion side, and then there's another one waiting on the aphelion, but we don't use that one. So that's the construction. This is some, we ought to have a nomogram kind of like this to go with this. We don't have that yet, as I recall. I never made one on the old programs. So anyway, that's the Kepler's geometry right there. It's giving rise to this and this, okay? And we're interested in the radius, which is all of that. So it looks like it's a horribly complicated thing, which we're going to have to integrate, okay? But it isn't that bad. As you put these things all together, it boils down fairly quickly. And I'm going to go ahead here and get this one on the time detail. This one makes it actually pretty simple. And the idea is that this thing boils down to just A epsilon cosine phi plus A squared. And that proves the construction. So the proof of this construction is a little more difficult than that one. That one's just basically geometry of sines and cosine. This one is this geometry of square roots of cosine plus a constant and times a constant. So that makes it a little bit harder. But in any case, that's the equation for this row right here. And we've got to integrate that sucker. Okay? Well, it looks like it's going to be a problem, but it isn't. It also cancels out fairly nicely. And it looks like it's going to be a mess, but it boils down to that. That's really neat. That is really cool. This is Kepler's equations of time, orbital time. Okay? And right here's the orbital period. The a to the 3/2 power, and then the square root of the ratio of mass to the Coulomb constant. That's neat. Okay, so that's kind of what's going on in all of these things. They're all covering up something that's has to do with the symmetry of a Coulomb field, the higher symmetry, the O4 symmetry, like orthogonal in 4 dimensions symmetry. we're going to finish up here just with going through, once again, the elliptical geometry and the hyperbolic geometry. Let's do the elliptical. We've already done a little bit, but here's something written out very carefully on a piece of graph paper with particular values for the constants. A is 4, okay? This ellipse is here. This is 4 units for the major, semi-major axis. And then the B, that's this thing right here, is half that, 2, okay? Then from formulas that we've had already, we can calculate the epsilon, the eccentricity, square root of 3 over 2, so that's less than 1, okay, 0.86, 0.87. And then the lattice radius for this one is a very nice 1, right there, okay. What else? There's the equations that relate epsilon to the ratio of B to A, which is 2 here. Okay, so that's what we got. Okay, so there's lambda over epsilon, there's R over epsilon, and so forth. Here's the other thing. The ellipse is really symmetric. So there is another focus which we don't pay much attention to because our gravity is all coming from here, and this is just an empty piece of dark space. But nevertheless, there is the other focus. You might call it the primed focus if this is not primed. I put the primes on this end. This is the apogee perihelion, and they go around a focal point there. Nobody is home there. There's something home here for sure. So that's kind of neat, but it does have that symmetry, and that's part of the story that we'll get into on Monday. But in any case, I have not only R over epsilon, but I also have R prime over epsilon. This is R prime. It's got to work both ways, right? It's symmetric. So you get to do the other side if you want to. Anything else I need to say? Not much, but I'm going to fill the board with some equations that we've already derived, but they're part of the story. There's the lambda equation right there, R equal 1 minus epsilon cosine phi. And that's part of the geometry. There's, for phi equal to 0, okay, this is just 1, so I get lambda over 1 minus epsilon. That's what basically, as this equation here would say, lambda is R times 1 minus epsilon, or R big is lambda over 1 minus epsilon. R little right here is just the opposite. It's a plus sign here, because that makes the thing very small. And you see, just with a 2 to 4 ratio for the A and B, I'm getting big ratios between this distance and the opposite of that distance. Okay, I'll let you figure out how it becomes R plus over epsilon. That's the big guy. This is a little bit less. Here's R minus, which is lambda over 1 plus epsilon. That's pretty obvious for this. This is R minus over epsilon. That distance right to from the directrix to the perihelion, the low point. And it's symmetric, so it's also happening on the other side. Major axis, the sum of R plus and R minus. Okay, any of these ratios here. What I can do there, see if I've got that. I go lambda 1 minus epsilon plus. Those are the two distances. R plus all the way to aphelion, R minus back to the perihelion. Okay, sum those guys up, and that's what gives you twice the half radius. So it gives you the entire distance from there to there is 2a. Okay. And then another equation kind of like that, has the differences. That works out kind of neat. To 2a times the eccentricity. So these are all relations that have physics behind them. I put physics on each one of those constants there. This is an important one just to see. This whole distance right here is A over epsilon. This distance here is just A times epsilon, so there's kind of reciprocal relation going on there. That A has to swing up to this point right there in order to match this. Let's see if I can see that. In order to make this equal to A. So that's an important thing about it. Unless if you swing a compass from its perihelion distance off of the minor axis, it's got to go through the focus. So you test to see if it's an ellipse, and then here's the test. Minor axis is right there, and I think that's about it as far as the geometry goes. But let's look at the family of conics, the whole family. Start with epsilon equals 0, circle, no eccentricities. Not eccentric, it's dull. But now we're starting to get a little eccentric. This is 0.65. This is 0.85. As I'm approaching 1, this is growing like mad. Okay? And finally, I work myself up to epsilon equal 1. Wow, that's a parabola that goes all the way down to Springdale, right? And then past there, right? That's forever, this parabola. But then what happens if you go epsilon bigger than 1? Well, that's kind of weird. Here I am with epsilon bigger than 1. Doesn't look much different from this, right? It's going to be a long time before I get a really eccentric hyperbola, right? And that'll keep getting smaller. But what's going to happen if this thing really were in real space and I was doing this? You see, I'm making epsilon larger. I keep making it larger. What happens? Bam! It hits me in the butt. It goes all the way to infinity and comes out through minus infinity and hits me in the butt. There's the other side. It's just a really big ellipse that's been wrapped around the entire universe, right? That's what two hyperbola branches are. That's a crazy way to look at it, right? But I don't think you'll forget it if you think about it. Anything hits you in the butt, you remember. Okay? So that's what it's going to do. It's going to hit you right in the butt. All right? So, okay, that's important to see. This is, knowledge about the conics that you can take home, so to speak. Now, all the rest of this is where very carefully I pick numbers. Here again, 2 and 1. This is a typical hyperbola. Now, this thing has hit me in the butt on this side, or if I was going the other way, that one hit me in the butt. There's symmetry. Okay? And it has this wonderful property of the lines that go between each of these circles that define the various parts of this hyperbola. And all of that is important. The eccentricities and lambdas, you've got to get a feeling for where they are. It's more than just an A measure from here to there, or 2A from there to there, but there's also a B measure. And how do you handle that? How do you think about the B? That we're going to really need if we're going to do Rutherford scattering, because that's going to be the impact parameter for a scattering event, which we will be getting. So if I turn the thing on the side, if I turn that rectangle on the side a little bit, so that its corner is right on the axis, then I get to measure B off of the line that goes from the center of this thing right up. That will be B equal 1 right there. That will be the impact parameter for a particle coming in and getting repelled by the center. This is a repulsive hyperbola that you would be looking at. Or, coming the other way, if there was a scattering center at the focus of this one, okay, this would be an orbit that came in with a opposite charge end going back out, attracted rather than repulsed. So these are all interesting things we'll talk about next Monday. There's another one going the other way. Okay, then you try something with an eccentricity here of pretty large, square root of 5, 2.3 or so, and you've got these left and right perigee points, right here and here. Very gentle sort of hyperbola now coming in. This goes back, hits you in the ass and crushes you. Got the eccentricity up so high. So I can turn that thing around and look at each of the interesting points that are associated with it. And we'll do that on Monday. But using a more powerful thing, the epsilon vector, is a really big deal for this. So these are all things that show the geometry of that really marvelous thing. Now the thing to know about the hyperbola is that the hyperbola, like the ellipse, could be constructed by having two strings come out of the focus points. The catch is that the strings have to come out and be able to lengthen. Otherwise I can't do a hyperbola. If I put a string here and here, and let's say it's that string right there and there, okay, if that was going to make an ellipse, the way it would make the ellipse is I would pin the string here and here, and then I would just go like that, orthogonal to the hyperbola. I would make an ellipse, right? Okay, so that's the orthogonal coordinate in the coordinates that we looked at that had hyperbolas and ellipses as the coordinates. The elliptic hyperbolic coordinate system consists of both this kind of thing and ellipses that get very eccentric here and less eccentric as we go up there. So there's the geometry of that. But in order for this one to work, to make this, I've got to let out exactly the same amount of string every time this one goes there. I've got to let out exactly the same amount on both sides. In other words, the difference between the string length here and here is the same as for this one and this one. And one that goes all the way to infinity and differs by that much, that's 2a right there. And there's 2a right there. Okay, so that's a little piece of, we'll go over that again on Monday, but that's a little piece of thing. And then also there's all the ratios that are in here. And this is a zigzag ratio maker, where I start off with a epsilon squared, and I reduce it by dividing by epsilon and then dividing by epsilon again. Here I start off with a b epsilon. I divide by epsilon, I'm sorry, I divide by epsilon to get a b, and then I divide by it again to get that. But the idea is every time you get a certain ratio, you strike off an arc and zigzag your way down, strike off an arc, zigzag down, and so forth, if you keep making this thing forever. So this is the polar version of our zigzags that we talked about before. And you see those ratios in this structure if you look carefully. Okay, so I say recall the geometric series zigzags. That was back in lecture 5. We did that on page 5 of that lecture. Okay, anyway, here's that table again, parameter table 7, page 79. Okay, just to remind you, that's the big one right there, that the A is k over 2e, or e is k over 2a. You can write it in either way. This e here is k over 2a. We had that table 79 up before. Okay, and I'm going to go ahead and bring this thing forward. And the reason I want to show you this one is, which is what we'll be doing on Monday, is we're going to take this diagram here and just rotate it so that it matches the one of the asymptotes of the hyperbola. I make that horizontal, okay, and then the hyperbola that we're going to be talking about that opened atomic physics to the world is one where an alpha particle sent from a long distance away, infinity basically, has come and been repelled here by this guy right here, okay? This guy is a gold nucleus, okay? And that's the target right there. And this particular beam had an impact parameter of about there. That's the asymptote of the trajectory that's coming in just above that thing now. It's been coming from infinity and each time getting a little higher, a little higher, a little higher, way back there. And then finally, we come into the scene here and it's this high because of its repulsion to that thing down there, all the way back there. And then, whoa, woof. That's the actual scattering event. Okay, so there's a preview of scattering of an alpha particle off of a gold nucleus, both positive. What if it's an anti-alpha particle? Okay, this is gold nucleus again, anti-negative charge, right? It comes from over there in infinity and keeps being dragged down below the asymptote, below the impact parameter of B, okay? And when it shows up on this screen, it goes zoof around there. And the anti-alpha particle, a negative charge, goes off that way. Or if it's an electron, okay, electron attracted, you better have a lot of energy to get by this guy. But if it has enough energy to be in the escape space, it would, and that would come out on this other asymptote here. So these two asymptotes just have to be rotated into position, and you see a beautiful way to see the geometry of that, and that's what we'll do, among other things on Monday coming up. Okay, that's it. I'm sorry if it is a fire hose of algebra, but that's the way this particular approach is.
So are we getting a new homework on Monday? Are we getting a new homework on Monday?